Ah, after solving many technical issues from part 1, I am now back with part 2 of Introduction to Line Loss and Voltage Drop Circuits. In this second of the series, we'll be looking at what happens when we have two loads that are connected in parallel. We'll be looking at the voltage that is lost in the lines, the voltage to each load. We'll look at the total circuit power. We'll look at how much power is lost in our lines feeding our circuit, and we'll look at how much power actually gets distributed to the load. With all that information, we'll be able to look at our circuit efficiency. So with all that being said, welcome to part 2. If you haven't already done so, please go back and look at the very first video. In the first video, we looked at the resistance of our wires feeding our circuit. And as we hooked up a load to our circuit and a current was starting to be drawn, we looked at various aspects of how this impacts the voltage at the load. Through that discussion, we went through a number of identities and we looked at what is the voltage lost in the lines, or our voltage drop. We looked at how we can calculate the voltage at the load, because it's a simple series circuit. And then we look at the total circuit power, the power that was lost in our feeder wires feeding our load. These are our power losses or line losses. Finally, we looked at the total power dissipated by the load, or the power delivered to the load. And finally, our circuit efficiency. If you are not familiar with this terminology, please go back and watch that video, because I am under the assumption that you are comfortable with these terms. As we go on and calculate and look at and examine multiple loops, we have to go back and do a quick refresher on Kirchhoff's current laws and basically our parallel circuit tenets, because that's really what we're working with now. We're hooking up multiple loads in parallel, but they have a series component that's going to consume some of the voltage and also cause some power loss. With parallel circuits, all the voltages are the same. Here I've got 5 lamps wired up, and each lamp is 60 watts each. Being 60 watts and 120 volts, that means that each lamp is going to draw a half an amp each. 5 branches at half an amp means that we're going to have a total of 2.5 amps for an IT. When it comes to our total power consumed in our circuit, we can just add up each of the individual powers. In this case, that's pretty easy since they're all the same, so it's just basically 5 times 60 or 300 watts. Our total current coming in is 2.5 amps. And we can calculate that as well from PT over E. Our 2.5 amps is going to come in and we're going to lose half an amp, which means we'll have 2 amps left. 2 amps is going to lose half an amp, which means we'll have 1.5 amps left. We'll lose a half an amp, which means we'll have an amp left. And that amp is going to split up between the 2 last branches of half an amp each. In branch 5, our half an amp comes along and then meets up with branch 4 again, where the 2 currents meet back up, which gives me an amp. That meets up with line 3 of another half, which gives me an amp and a half, which meets up with branch 2 of another half amp, which gives me my 2. And then that 2 meets up with line 1, where we get our other half to get our IT back of 2.5 amps. We have to understand this concept of how the current breaks up between the branches, or adds, depends on which way you're looking, and the distribution of the currents. We also have to take with us to help us solve these problems that powers add, or the load powers add, and that all the powers together have to add up to the source power. The plan with the next set of voltage drop problems is to look at 2 loads connected in parallel. In this example, load 1 is going to have 12 amps and load 2 is going to draw 6 amps. Here's a simplified schematic to help us work through our circuitry. And again, our total current is going to come in and branch off between load 1, and load 2. Since load 1 is going to draw 12 amps and load 2 is going to draw 6, that means our total current is the sum of those two currents. That's Kirchhoff's current law at work. And this is what we need to think about and keep track of as we continue to solve this type of problem. So let's take this circuit and continue to work with it and go through the solution for all our voltage drops, our line losses, and powers to and voltages to our loads. So looking at our circuit and how the current breaks up into load 1 and load 2. Knowing what our loads are, we can calculate what our IT is. IT is going to be made up of our 12 amps in load 1 and our 6 amps in load 2, which is going to give us a total current of 18 amps. Knowing that we have an IT of 18 amps, that's going to be flowing through R1 and R2, which represents the resistance of our feeder wires going to load 1. 18 amps times 0.2 ohms means we're going to lose 3.6 volts in each wire, for a total drop around this loop in our feeder wires of 7.2 volts. In our loop 2 in the back, I've got 6 amps flowing through this end. 6 amps through our feeder resistance of 1/4 ohm each means that I'm going to lose 1.5 volts on each wire for a total loop drop of 3 volts. Knowing our voltage drops due to our feeder wires, we can now calculate how much voltage is going to be at each load. I started off with a 120 volt source. So by the time I get to load 1, I've lost 3.6 and 3.6 in this loop, which leaves me with 112.8 left over. That's employing Kirchhoff's voltage law of sum of voltages around any one current loop must add up to the source. In the back loop, I've got 6 amps flowing through my wires, dropping 1.5 volts each. But this back end is in parallel with load 1. So you can look at load 1 feeding this back branch. So 112.8 volts, take away 1.5 volts and 1.5 volts, 3 volts, is going to leave you with 109.8 volts in this second load. You could also go around the whole outside if you wished. So 120, take away 3.6, take away 1.5, take away 1.5, take away 3.6, leaves you again with your 109.8. It's just a different way of looking at it. I need to turn off that. So now we've calculated all our circuit voltages and we have all our circuit currents. We can calculate all the powers. So in our first loop, let me get a pointer here. Our first loop, we had a total voltage drop of 7.2 volts. We know that we got 18 amps running in those two branch feeders. So that'll give us 129.6 watts of power lost in our feeder wires. So that's the cost of doing business. That's how much power just the wires are going to consume to feed our load. In the second branch, I've got a 3 volt loss at 6 amps, which means I'll have only 18 watts worth of power lost in these two wires. That's 9 watts apiece. When I sum those together, that means I've got 147.6 watts of power wasted just in my wires feeding my circuit. And this is why we have to size wires accordingly to reduce our voltage drop and reduce the amount of heat generated in our wires. Bigger wires, less resistance, less I squared R losses. We know that we've got 112.8 volts to load 1, and it draws 12 amps, which means we've got 1353.6 watts of power being dissipated in load 1. Following the same procedure for load 2, it means we're going to have 658 watts dissipated in load 2. So the total power to our loads is just the sum of those two, which in this case gives us 2012.4 watts. We can now calculate the total circuit power because, well, we could have from the start. We've got 120 volts, 18 amps, which means we've got 2160 watts of total circuit power. Since we've got the output power of 2012.4, our total input power of 2160, we can now calculate out the circuit efficiency by power out over power in, or power to the load over power total. And our overall circuit efficiency for this example works out to be 93.166%. So let's do one more problem. Now, if you would like, you can pause the video here and work your way through the problem, finding all the voltage drops, the voltages to each load, the power lost in the feeders or the wires, power dissipated by each load, as well as the total circuit power, and finally the circuit efficiency. So if you'd like to work on it on your own and then check your values, by all means pause the video here and then follow the solution. So for those of you not pausing, or if you paused, let's work through this problem real quick. The first thing I need to do is look at my total circuit current, Kirchhoff's current law. 8 and 6 gives me 14 amps. Knowing that we got 14 amps in our first loop, that's going to give us 1.4 volt drop on each wire for a total of 2.8 volts drop in our first loop. 120 take away 2.8 gives us a load 1 voltage of 117.2 volts. Knowing that the back loop is fed from the first loop, we can use that value to carry on and solve the second loop's values. So our voltage drop in our second loop works out to be 1.2 volts each wire, or 2.4 volts. 117.2 take away our total loop voltage drop, leaves us a remainder of 114.8 volts to load 2. Now that we got all our voltages, currents, we can find all our powers. Total power, ET/IT, we should have 1680 watts total coming in. Load 1, doing V load 1 and current 1, should give us about 937.6. Our load and power 2 should give us about 688.8, which means our total load power is about 1626.4. We could calculate all the individual losses, or we could just take the difference of our total power and our total load power, which leaves us with 53.6 watts. With that information in hand, we can calculate our circuit efficiency, and for this example, it works out to be about 96.8. So hopefully, if you worked yourself through that, you get the same answers I did. Or hopefully, I got the same answers you did. So, this is the summary. We looked at a 2-loop voltage drop problem. We started off by using Kirchhoff's current law to solve for our currents. We then, once we had all our currents, we solved for all our voltage drops. And with our voltage drops, we could find our voltages to our loads. And with all our voltages and currents in hand, we were able to solve for all our powers. This pretty much brings us to the end of the second video in the series, which helps us find our overall circuit efficiency. Hopefully, coming soon, in part 3, we'll build on all of these principles and we'll look at the Edison 3-wire circuit. This is the type of circuit that you have in your residential circuit panels, where you got 120, 240 feeding your household loads. So, thanks for watching. I appreciate it. Don't forget to like and subscribe. And if you enjoyed this video, don't forget to give it a hairy thumbs up. And I'll see you in part 3 sometime down the road. Don't forget, there are plenty other videos on this channel that have to do with circuit fundamentals, PLCs, and I'm continuously adding videos as I need to. So thanks for your support and have a good one.